That was awkward. I'm as dope as 2 rappers. You better be scared, cause that means Albert E equals MC squared.
You've got no idea what you're messing with here, boy. I got 12-inch rims on my chair, that's how I roll, y'all. You look like someone glued a mustache on a troll doll. I'll be stretching out the rhyme like gravity stretches time. When you try to put your little pea brain against this kind of mind. On the best, on the Snoop Dogg science, I'll be dropping mad apples on your head from the shoulders of
I was a giant whose shoulders you'd have stood on if you could stand. I'll give you a brief history of pain with the back of my hand. You can't destroy matter or me, for serious. Ripping holes in you bigger than the hole in your black hole theory was.
There are 10 million, 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 million particles in the universe that we can observe. Your mama took the ugly ones and put them into one nerd. You wanna bring the heat with the mushroom clouds you're making. I'm about to big raps from scratch like Carl Sagan. And while it's true that my work is based on you, I'm a supercomputer, you're like a TI-82. Ooh.
So each particle, as you can see, has a certain amount of mass and a certain amount of energy associated with it, called the rest energy. And this comes from E equals mc squared. And this is based off of Einstein's special theory of relativity in 1905, where he predicted the equivalence between mass and energy. So how does this work? E is energy, and it's in joules. M is mass defect, or just mass, and that's kilograms. And then C is the speed of light, which is always the same thing as 3 times 10 to the 8th. So when we have 1 kilogram of petrol is burned, 5 times 10 to the 7th joules of energy is released. What mass would this represent? So 5 times 10 to the 7th is my energy. I'm looking for mass, so even though it says 1 kilogram of petrol, I'm looking for what this represents in the energy. So I always know what C is. It's 3 times 10 to the 8th. So I'm going to plug in what I know. I'm going to go ahead and square that, and then I divide it out, and I get 5.56 times 10 to the negative 10th kilograms of mass. And so that's how much that amount of energy would represent. Okay, so 1 U approximately is equal to 1.66 times 10 to the negative 27th kilograms. Okay, that if I have an amount of mass that disappears, that would be equal to 1.49 times 10 to the negative 10 joules, which is not very much energy really. So they have a different unit for energy called an electron volt. It's a little bit smaller. It represents 1.60 times 10 to the negative 19th joules. So there's your conversions. So that's where that MeV came from. That's electron volts. And so if you lost 1 U, which would be about a proton or a neutron, that would be equivalent to 931.5 mega electron volts of energy. So let's do a couple practice questions. When 1 kilogram of uranium-235 undergoes fission, 8 times 10 to the 13th joules of energy is released. What is the decrease in mass in kilograms and atomic mass units? So let's look at kilograms first. We know that the energy is 8 times 10 to the 13th. We're looking for mass. I'm going to plug in my speed of light, square it as always, divide it out, and I get 8.9 times 10 to the negative 4th kilogram. So that's the equivalent mass and energy. So now I could do this, what I can do here is I know that for every atomic mass unit I have 1.66 times 10 to the negative 27th kilograms. So I can actually just set up a proportion and then I can cross multiply and divide. So I'm going to get, when I cross multiply, 8.9 times 10 to the negative 4th on one side and 1.66 times 10 to the negative 27th times x on the other side, divide it out, and that's going to give me the equivalent in atomic mass units. Okay, so how does nuclear stability fall into this? Okay, this has to, again, to do with the strong nuclear force. So if you look at this graph, it represents a stable nucleus. You can see all the dotted lines there represent stability. As the number of protons increase, there's more and more positive charge in that nucleus, and so it's pushing to repel even more. And so they're only going to be stable if they have more neutrons than protons to have enough strong force, because that's where the strong force is coming from. So, and remember that, again, as they get bigger and bigger, that's a problem because strong nuclear forces work only on very small distances. So as the number of nucleons increase, nucleons are protons or neutrons, then the size is also increasing, which is a problem. So how that works is, if it's above 83, number 83 on the periodic table, which is bismuth, they cannot overcome that by adding more neutrons. So that means that anything over 83 on the periodic table is not stable. So what does that mean? To break apart the nucleus, energy has to be added to overcome the strong nuclear force. And so that amount of energy added is called the binding energy. You can think about how much energy it takes to bind that nucleus together. A different amount of energy is used when the nucleus is bonded and when it's separated. It's not the same. So the difference in energy is called the mass defect. So that again is where E equals mc squared comes in. If you look at the mass of the parts on the left and the mass of the alpha together on the right, they are not the same, and that difference is the mass defect, and that can be used to calculate the binding energy. Okay, this also applies in fusion. Okay, if you have two nuclei such as hydrogen or deuterium fusing together in fusion, they're going to make one bigger nucleus. There's going to be binding energy in that situation. The difference in binding energy between the reactants and the products is going to be released. So if we look at this example, we have the weight of the hydrogen, the weight of the deuterium, and we add those together. Okay, and now if we look at the weight of the helium on the right side, those are not the same, and they should be. So where did that extra mass go? That's your binding energy. So that if you subtract them, that was the difference in mass. The energy released can be calculated from E equals mc squared, so I just put that mass in there. I have speed of light as always, 3 times 10 to the 8th squared, and that's where the mass went. It went into 8.8 times 10 to the negative 13th joules of energy. That would be the measured energy release. Fission is when it splits apart. You have a heavy nucleus. It is unstable because an extra neutron goes in there and it splits into two lighter nucleus, smaller nucleus. And again, the total binding energy of both of these is greater than the original. So the difference in energy is released. Okay, so fission is an exothermic reaction. That missing mass, usually the sum of the nucleus that come out of there is less than the original, and so that missing is because it's converted to energy, and E equals mc squared.